In this video, we will see what the gain bandwidth product, one of the figures of merit of an amplifier, is. We'll analyze the frequency response of an op-amp and explore its speed limitations. So far we have not considered frequency as a factor in any of our analysis. That is, we've considered the gain of the op-amp to be constant for any value of signal frequency. In reality, due to the internal capacitances of the op-amp, the value of gain degrades for higher values of frequency. Typically, as shown, the gain of an op-amp remains constant up to a certain value of frequency. We call this value the cutoff or corner frequency of the op-amp. The range of frequencies for which the gain of an op-amp remains constant is referred to as the bandwidth of the op-amp. After the cutoff frequency, on a log scale graph, the gain reduces at a rate of 20 decibels per decade. For simplicity, we can model the internal circuitry of an op-amp as a single pole system. If the pole is at omega naught, the transfer function becomes A naught, upon 1 plus S by omega naught. Hence, at frequencies well below omega naught, the gain of the op-amp is A naught. Note that the corner frequency for a first-order system is given by the value of its pole. The gain decreases as the frequency crosses omega naught and eventually falls to unity at the frequency, say omega u. This frequency is called the unity gain bandwidth of the op-amp and has a value of A naught, into omega naught. That is, the unity gain bandwidth is the DC gain multiplied by the cutoff frequency. Hence, it is also known as the gain bandwidth product. The unity gain bandwidth is typically considered as a figure of merit for an amplifier. Till now we have been analyzing an open-loop op-amp. Now, using our newly developed model, let's analyze an op-amp in a closed loop. Consider a non-inverting amplifier. If we consider the gain to be finite, the gain is given by A upon 1 plus, R1 upon R1 plus R2, into A. We replace A by the single pole model mentioned before. Substituting A naught, upon 1 plus S by omega naught in place of A, we get the following expression. Multiplying the numerator and denominator by 1 plus S by omega naught, and rearranging a bit, we get. This is a first-order system with the pole at omega naught, into 1 plus R1 upon R1 plus R2, into A naught. The DC gain is now A naught, upon 1 plus R1 upon R1 plus R2, into A naught. Hence, the closed-loop gain is significantly smaller than the open-loop gain while the closed-loop pole is much larger than the open-loop pole. Hence, we have a trade-off between gain and bandwidth. If we wish to increase one, we must reduce the other. Let's try to find the unity gain bandwidth of this circuit. We already found out that the unity gain bandwidth is given by the product of the DC gain and cutoff frequency. Multiplying these two, we get omega u as A naught into omega naught. This is exactly the same as before. Hence, placing the op-amp in negative feedback does not seem to affect the unity gain bandwidth. In the figure shown, the yellow curve represents the op-amp in open loop and the red curve represents the op-amp in closed loop. In other words, the gain bandwidth product of an op-amp is the same, irrespective of whether it is an open loop or closed loop. That's all for the frequency response and gain bandwidth product of an op-amp. If you have any questions, please ask in the comments section below. Don't forget to like, share and subscribe.